All right, so the last time we met, basically what we talked about was inelastic collisions. So today we're going to talk about elastic collisions. Um, so elastic collisions are theoretical. Most real collisions are somewhat inelastic. There's nothing that's really 100% elastic. But basically, the short of it is, um, for an elastic collision, the kinetic energy is conserved. So, yeah, you gotta write all this stuff down. Now, when I do this, there it is. So, elastic collisions, the kinetic energy is conserved as well as the momentum. So, if you remember last time when we talked about inelastic collisions, basically the momentum was conserved, but the kinetic energy wasn't. And that's one way you could tell. Another clue is if they stick together. The two objects, when they stick together, that uses up some of that kinetic energy. It doesn't use it up. It's just they have the same velocity. So the kinetic energy isn't conserved. The energy is conserved for sure, but the kinetic energy isn't. All right. There was another thing I was going to mention, but I forgot what it was. So one way to tell if the collision is elastic or inelastic, you basically check the momentum at the beginning and the end, the initial momentum and the final momentum, and then you also check the kinetic energy. So for your homework and on the test, I'm going to give you a problem. The momentum will always be conserved, right? But then you got to go back and double check the kinetic energy. If the kinetic energy is conserved, then it's elastic. Okay? The energy is conserved. It's just we're only focusing on the kinetic energy. Okay? So I'll give you guys a couple seconds. I see some of you writing down these formulas quickly. All right. Today's episode of Physics is brought to you by Fairlife. When I first started recording these YouTube videos, one of my students' parents, he worked for Contigo. In fact, I think he was like the CEO or the vice president. I can't remember. And I used to drink a lot of coffee, and so for a Christmas present, they brought me in a Contigo mug, and there was a lot of shots. And then his daughter wanted me to give them a shout out, so we used to do that. Well, actually, today I have my Duneland Media mug. All right, do we have this? Okay, here we go. All right, so just write the words down and sketch this out real quick. So remember, conservation laws, the momentum before the collision equals the momentum after. The energy before the collision equals the energy after. And so remember for energy, and I want you guys to write this down too. The types of energy can be kinetic, actually, let me write that some other place. I'll write it up on the top here so you guys can see it in the back. So when we're talking about energy, there's lots of energies. So kinetic is one type of energy that we're going to focus on. Remember, kinetic means moving. There's potential energy. Potential. Sorry, guys. Oh, this is so annoying. Oh, no, I've done broke it. For some reason, that looks like it's spelled wrong. But what were some other energies that we talked about? Potential energy, kinetic energy, heat. Okay. So the energy is conserved, but it's not always going to be kinetic, right? So the energy is definitely conserved in any collision, but for the elastic ones, the kinetic energy is conserved. So this is a little bit different. When we did conservation of energy problems, we thought about all the energies. Oh, rotational energy. I forgot about rotational. That was the one I was like, what? Okay. And there's others. Can I move on to the next one? All right, cool. So you don't have to write this down because you already have it in your notes. So perfectly elastic means the objects stick together for the whole time, right? They don't move. Inelastic collisions, they're somewhat bouncy, so they stick momentarily. So the reason you have a gap here, these two paths represent the kinetic energy in a roundabout way. The more kinetic energy it has, the higher the ball will bounce. And if all of the kinetic energy is conserved, it will bounce as high as it was the original height it was dropped from. But the reality of it is when the ball hits here, it squishes a little bit, it sticks to the floor for a little while, and then it bounces up. That's why you have this gap here between the elastic or the inelastic and elastic. This is what 90% of your collisions will be in the real world. And elastic is perfectly bouncy. So that means basically the kinetic energy is conserved. Okay, it doesn't. The sticking part uses up a little bit of energy. Some of that energy is transferred or transformed into a different form. All right. So momentum is conserved in all three collisions. What's different about them? Write down this last line. One of them also conserves kinetic energy. Which one? Elastic. So this one right here, so you could just write elastic right here. So one of them conserves kinetic energy, and that's elastic. I don't know why we say perfectly inelastic when we should say perfectly elastic, because a true elastic collision is almost impossible. There's always a little bit of sticky. Oh, this is for way later in the day. I hope I remember that. I'll forget. This is for fifth hour. Oh. Okay, can we go? Let me move my face. Write down the words here. So, elastic collisions, the total kinetic energy is conserved. For inelastic collisions, kinetic energy is not conserved. And you only have to write down what I highlighted. So it says some of it is transformed into other types of energy, such as thermal or heat energy. I guess you should call it thermal energy. And sound energy. So when something smacks together, you hear a sound. Well, this sound actually is moving air molecules in a way that causes vibrations, and those vibrations your ears pick up, and that's how we hear sound. But we're physically moving air. And so work is being done. Work is equal to energy, blah, 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 blah. Does that make sense to you guys? Okay. That's why when there's a loud, or let me back up, when there's a big collision, it's very loud, right? Because there's more energy. There's more energy, and so because more of that energy can be transformed, it's going to create larger sound waves, so it'll be louder. Okay? Same with thermal energy. Although we do have some very they're not even microscopic. They would be like nanoscopic. But we have some, like a nuclear reaction. Nuclear reactors release a ton of heat. Yeah. Not only in the nuclear reaction itself, but the bombardment. Yeah, it's a bit. All right, can I move on to the next thing? Not yet. I wonder if it's easier if I do this, if I zoom out a little bit and then move this up. I mean, is that easier for you guys way in the back if I move this up like this? Does that help? Is it a little easier? No? What about now? Can you see it? Can you see the bottom? Sort of. What about the very back row? Can you see the bottom? Yay, nay, no? All right. Well, nobody's awake yet. Can I move on to the next thing? All right, cool. So inelastic collisions conserve momentum but not kinetic energy. So you guys can jot that down real quick. Now remember, I know we're kind of stating the same stuff over and over, and I want you to write it down simply because I got to get it in your brain 27 times. The more times I cram this stuff in your brain, the more likely you are to remember it, right? Because you're going to take a test, and I'm going to have a question on there. Is this collision elastic? And you got to know off the top of your head, elastic collisions. Momentum is conserved, but also the kinetic energy. You got to know that, right? So the more times I can cram it in your brain. In the moment, when I say it one time, you're like, duh, I get it. Why does he keep repeating himself? But will you remember that when we come back from spring break? Also, just quit complaining. Actually, you guys are good kids. You don't complain. It's those other kids. All right. So real collisions in the real world are inelastic. Okay? It happens. There isn't anything. Now, there are some things that are pretty darn close to elastic. It's kind of like friction. All the problems that we do, we say ignore friction. Well, we're going to do some problems, and we're going to pretend that this elastic stuff can happen, right? But the macroscopic objects are inelastic. That means kind of, regular stuff. Okay? So like a bouncing ball, stuff like that. If you play pool. All right, can I move to the next thing? Think of how loud it is when you play pool. If these collisions were totally elastic, the ball would bounce forever. So you've never dribbled a basketball one time and then it just keeps bouncing forever, right? There's too much stuff in the real world. Okay. You don't need to write this down. I'm just trying to show you some stuff. So collisions between gas molecules are elastic. I think because they don't really they're what we call a non-contact force. So make sure that you write this down. So write down. And the reason they're that way is they're non-contact, right? So they're non-contact. We were talking about them, and I don't know if you remember that or not. We were talking about how they repel each other, right? Yeah, like magnets. So they have like charges, so they push each other apart. So when they collide, they never really actually make contact. So in order for you to make sound or thermal energy, you have to actually touch. The molecules of one item have to touch the molecules of another. And I suspect there are some nuclear things too. But like I said, nuclear reactions, we actually explode the nucleus of an atom, and then there are subatomic particles that come out of that, and they physically collide. But I wonder though if they actually make contact. I don't know. I'd have to think that through. But I know that there's particles that bombard each other, like they're going to run into each other. Okay. A near miss, and there's no good place to put my face. Near miss collisions between a comet and the sun are also elastic. Again, the reason, you don't need to write this one down. You can if you want to. But the reason they're that way is they're non-contact. There's no physical contact between them. So if you remember a while ago when we said there's a collision, there are forces at play, right? Well, these are non-contact forces that are at play. Gravity, electromagnetic, stuff like that. And like I said, you don't need to write that down. All right. Collisions between billiard balls are nearly elastic. Nearly. So you need to write this down. Not 100% though. It's what we would call negligible, right? So remember when we did the t-shirt launcher, and I said, what do we need to consider when we try to calculate where this t-shirt's going to land? And everybody said, raise their hand, and correctly said air friction, right? Yeah, air friction does come into it. But if we calculate the air friction, it makes our measurement 2 or 3 inches more precise, right? So if you're going to shoot a t-shirt across a football field, air friction does have an impact on the path that the t-shirt travels, but it's what we would call negligible, right? It's like, if it's a couple inches short, even if it was off by 2 feet, you're shooting it into the stands. Same thing with the billiard balls. Because of the table size and the amount of energy that you're able to hit that cue ball with, you're going to lose a little bit of that kinetic energy, but not much. Not much. Okay. All right. You don't have to write this down, but I had a thing like that, but through the course of the year, you guys kind of broke it because you kept playing with it. It's not really well constructed, but these pendulums, this is a popular toy. If you take one ball, the one ball goes back and forth. So if I take one ball up, run into the other ones, only one comes up. If I take 2, then 2. If you were to do 3, 3. They're nearly elastic because the kinetic energy transfers. But and they go for a while, but eventually they stop, right? Okay. Gravity has a lot to do with that. But they're nearly elastic. They still make a sound though every time they hit each other. So that sound. Same with the billiard balls. When those 2 balls touch, they make a loud sound. The harder you hit the ball, the louder the sound. Okay. And man, I'm just going to turn this off. An elastic collision, and like I said, I know that we've written this down a lot. Write it down again. An elastic collision conserves momentum and kinetic energy. So we're going to do a problem that we've done before, and we're going to determine if it's elastic or inelastic. So Mr. Adams is not losing his mind and repeating himself. I'm repeating myself so I could get it in your brain 27 times, right? He just keeps saying the same thing over and over. Can I move on to the next slide? Yes, Mr. Adams. All right, here we go. This is the part you love. So conservation of kinetic energy. Here we have two balls colliding. So this is the initial part right here, right? Let me change that. So this right here is this initial part, the before. All right. And then there's a collision somewhere in here. And then this is the stuff afterwards. That's the after. Okay. And where the equal sign is, that's where the collision is. Okay. So when we have a collision, whether one ball, and this is, I'm going to add to this. Remember, when you do conservation of kinetic energy, in this scenario, the red ball is sitting still. The green ball collides into the red ball. That's the same thing that we did yesterday. But remember, for your conservation of kinetic energy, you could think of it like this. You have the kinetic energy initial is equal to the kinetic energy final, right? So then you would have 1/2 times the mass of the first object, times the velocity of the first object squared plus 1/2 times the mass of the second object times the velocity of the second object squared. And these are the initial velocities, so put a little I in there. That has to equal 1/2 times the mass of the first object times the final velocity of the first object squared plus 1/2 the mass of the object. Second object times the final velocity 2 squared. And here they did it different, right? So remember that VI sometimes is written as V naught, and V final then is sometimes written as just V. So they wrote it the second way, right? This is how they wrote their formula. Okay. And it's just keeping track of the initial and the final. I'll give you guys a second to write all that down. So because the red ball wasn't moving, the second object wasn't moving, this whole thing was equal to 0. And that's where this came from. I want to show you guys that because there'll probably be a homework problem where you have to know that. Okay. Oops. You guys have that part written down? All right, let's go to this one. It says, in elastic collision, the total kinetic energy before the collision is the same as the total kinetic energy after the collision. Okay? So the key word there is total. You don't have to rewrite this, just kind of pay attention. Remember, the key word is total. That's why Mr. Adams wrote it down like this. What I did is I wrote down the total kinetic energy and the total kinetic energy. The total initial and the total final. Okay. Now, in an elastic collision, the kinetic energy gets used up a little bit, so the final is less because it gets converted to thermal and sound and a bunch of other stuff. But those are the two main ones. Okay? So it's going to be a little bit less. Again, you don't have to write this down. I just want you to look up at the screen and pay attention. All right. So what's the difference between elastic and inelastic collisions? Somebody want to tell me? Well, elastic, and you need to write this down, elastic, momentum, and we probably should say total momentum. Momentum and kinetic energy. Kinetic. Are conserved. Inelastic, momentum is conserved. Again, we should probably say total. But kinetic energy is not. Does everybody have this written down? All right. So let's do the same problem. So this is the same problem that we did before, and it's asking us if it's elastic or not elastic, right? Inelastic, right? So the question is, we have a 10 kilogram ball. And it's moving with a velocity of +3 meters, strikes a stationary 10 kilogram ball. If the collision is elastic, what are the velocity of the two balls after the collision? These balls have an equal mass. So this is the type of question. So this is an interesting question because, shoot, I changed it. There we go. I can't see the yellow. So because it's elastic, that means that there are velocities of the two balls. So we've got to figure this out. So I have M1 moving at 3 meters per second. And M1 has a mass of 10 kilograms, right? 10 kilograms. And then I have M2, which is also 10 kilograms. It's going 0 meters per second. So that's the before. After, I have M1 and M2, and we're trying to figure out what's going on with the masses. So we said that if it's elastic, then the kinetic energy is conserved. So the kinetic energy over here is 1/2 M1 times V1 squared plus 1/2 times M2, and this is the initial, M2 V2 initial squared is equal to 1/2 M1 final velocity squared plus 1/2 times M2 times V2 squared. And these are the finals, right? Okay, well, this is going to, because this mass or this velocity is 0, this whole thing goes away. So I'm going to have 1/2, well, let me back up. If I multiply everything by 2, guess what happens? All of these 1/2s will cancel. If I multiply everything by, or divide by 1/2, but I can get rid of all of those. Another clue is that because they have the same mass, right? This is 10 kilograms and this is 10 kilograms. That means that M1 is equal to M2. So I can come in here and I can change this to M1 and leave this as M1. So I end up with M1 V1 initial squared is equal to M1 V1 final, right, squared, plus M1, right, because it's the same thing, so I could substitute M1 in here, V2 final, squared. All right, now when you combine those together, again, well, I don't need to, watch. If I divide everything by M1, divide everything by M1, and divide everything by M1, well, then I just get VI initial squared, and that's of the first one, is equal to V1 final squared plus V2 final squared. And so let's do that up here. So I'm going to write that down up here. So I'm going to say 3 squared has to equal V1 final squared plus V2 final squared. Now, since they don't stick, those velocities are going to be different, right? So this is going to have to be 9 is equal to whatever this is squared plus whatever this is squared. Okay? So then how do I go back and find out what this is? Well, I'm going to have to use the conservation of momentum. That's what we talked about last time. Whew, that's a lot of stuff to write out, right? So we're just going to put a pin in this for right now. Now, if I were to guess, because they have the same mass, I feel like what we're going to end up having is, I feel like V1 final squared is going to end up being something like 4.5, and V2 final squared is going to end up being 4.5 because they have the same mass. I feel like that's what's going to happen. But one of them will be positive and one of them will be negative. So this first one will probably go back negative. But we need to verify that. Why do I... Oh, wait, it can't be that. It has to equal 9. So, ooh, I can't guess that. Why I just did what you guys did. Or would do. All right, so now we got to go through and do the conservation of momentum. Oh, that's a lot of work. So let's do that in purple. So I've got M1V initial plus M2V 1 initial 2 initial should be equal to M1V 1 final plus M2 V2 final. All right, since M1 equals M2, we could divide all of these by M1, right? So if I divide all of these by M1, in other words, I'm going to replace this with M1, I'm going to replace this with M1, and I'm going to divide all of these with M1. So then I have V1 initial plus V2 initial is equal to V1 final plus V2 final. Well, the velocity of this is 0, so I end up with V1 initial is equal to V1 final plus V2 final. We know that this is equal to 3. Now we're going to have to substitute this into this one. So before I substitute it in, I'm just going to subtract. I'm going to solve for one of these. So I'm going to subtract V2 final, and I'm going to subtract V2 final. And so the thing that I'm going to substitute in is 3 minus V2 final is equal to V1 final. So I'm going to plug that in right here. Well, actually, I'm going to plug it in. Got to be careful how I do that. I'm going to plug that in right here. So I'm going to take that equation, and I'm going to say over here, I'm running out of space, 9 is equal to, and then in parentheses, I'm going to plug in this stuff here for V1. So I'm going to say 3 minus V2 final squared plus V2 final squared. So this is an interesting thing. So this is a quadratic. We got to multiply it out. That's the same as 3 times V2 final times 3 minus V2 final. So you end up with 9 minus 3 V2 final minus 3 V2 final plus V2 final squared. So then this whole next line becomes okay. Then this whole next line becomes, we're almost done, guys, with our notes, by the way. This is going to be, if I write it in order, I'm going to say 9 minus 3 plus minus 3 is minus 6 V2 final plus V2 final, and then we got to tack on the plus V2 final. So this is a little more algebra intense. So then if you simplify everything a little bit, I have 9 is equal to 9 minus 6V2 final plus 2V2 final. Okay? Now to solve this, I'm going to have to subtract 9 from both sides. And I end up with 0 is equal to, and I'm going to rewrite this in ascending order, 2V, and this is supposed to be squared, 2V final squared minus 6V final. And so then you can factor out a 2. This is actually easier to solve than you realize. I'm running out of space here. If you move this over to the other side by adding this, my next line would be 6V2 final is equal to 2V2 final squared, right? So then I'm going to divide this by 2V2 final on both sides, 2V2 final. This 2 cancels with this 2. This V2 final cancels with one of these. This reduces to 3. This V2 final cancels with this, so we get 3 is equal to V2 final. Whew. All right. So then, because I have this, so that's the final velocity, then I got to go all the way back over here to this one, and I'm going to say 3 minus 3 equals V1 final, right? And so then from that one, I end up with my final velocity of the initial is 0. So what does that mean? That means this becomes 0 meters per second, and then this one travels with 3 meters per second. Wild and crazy. And that looks very confusing. Sure hope you guys are paying attention. At least 2 of these questions will be on your test. So you got this. It's just algebra. So the final answer is V1 not, or V1 final is equal to 0 meters per second, and V2 final is equal to 3 meters per second. How you guys feel about that? Thumbs up, thumbs down on that one. I'm not expecting a lot of thumbs up on that one. That's pretty algebra, and but it's just algebra. But it's some extra level stuff. So because it's elastic, the kinetic energy has to be conserved. And that kind of makes sense, right? The full kinetic energy gets transferred from the first ball to the second one, right? I'm assuming, yeah, right? Does that make sense? That's the only way that kind of works. Because if they were to separate and go in opposite directions, one of them would be positive, one of them would be negative. That won't work, because that'll add up to 0. And then I was thinking, well, what if one is, what if the difference between the two is 9? Well, you really don't know. You can't guess. You got to go through this math to figure that out. Okay? Can I move on to the next slide? All right. So, after the collisions. All right. So let's try to do this one. This one will be a little easier. So it says that you have a 1 kilogram ball. All right, 1 kilogram ball. Oh, shoot, I got to get the right color here. 1 kilogram ball moving with a velocity of 1 meter per second strikes a stationary. What does stationary mean? 0 meters per second. It strikes a stationary 3 kilogram ball. The two balls stick together and move at a final velocity of positive 0.25. Was this an elastic collision? Well, I don't need to do any math on that. What's the answer? No, they don't stick together. But let's go through two things. Let's do the momentum. All right, so I have M1 V1 initial plus M2 V2 initial has to equal M1 plus M2, right, because they stick together, and then that's the final velocity, right? Remember that? When they stick together, they have the same final velocity, so we set it up this way. So now we just plug the numbers in, right? So this is M1, this is V1 initial, this is V2 initial. Stationary means 0 meters per second. This is M2 right here, and this is MV, or I'm sorry, V final. So let's plug in the numbers, okay? So it should work out mathematically. I've got 1 times 1 plus 0 times 3 should equal 1 plus 3 times 0.25. So over here, this goes away to 0, and I have 1 times 1, which is 1, is equal to 4 times 0.25. Well, what's 0.25 times 4? 1. So the momentum's conserved. Now we got to do the initial kinetic energy times the final kinetic energy. So this one's going to be 1/2 M1 V1 initial squared plus 1/2 times M2 V2 initial squared has to equal 1/2 M1 V1 final squared plus, and the trick to this is, well, I'll just write it out and then we'll plug them in. To what the heck is going on with this thing? To V2 final squared. All right. So if I multiply everything by 2, I end up with M1 V1 initial squared. Now the second velocity is 0, so this whole thing goes away to 0, right? And then over here I have M1 V1 final squared plus M2, this should be plus, M2. Now they have the same final velocity, right? So this is M1 final, which is also equal to V2, not M, V2 final equals V1 final equals the final velocity. So I'm just going to change this to V final, and over here this will just be V final squared. Okay, so now I plug it in. I've got my first mass, which is 1, times the initial velocity, which is 1, squared is equal to 1 times 0.25, which is squared, plus M2, which is 3, times 0.25 squared. Okay. So this is going to be 1. Remember that 0.25 is the same as 1 over 4, and 1 over 4 squared is equal to 1 over 16. So this is going to be 1 times 1 over 16 plus 3 times 1 over 16. So I end up with 1 is equal to 1/16 plus 3/16, which is equal to 4/16, which is equal to 1/4. Well, they don't equal. So the kinetic energy is not conserved. Okay. So this is definitely, was it elastic? No, we knew that because it stuck together, but because the kinetic energy was not conserved, we would say it's inelastic. Okay, and that's it. That's all we're doing today.